Hello students, we're going to review practice problems 3, 4, 5, and 6 from E.1. E.1 is all about structure of the atom, and specifically we're going to start off talking about the energy levels of an atom. Number 3 says the diagram shows some of the energy levels of an atom. It's important that you understand that the energy levels of an atom here are showing that the bottom level is the most negative number, and then as an electron absorbs energy, it goes up levels, and so that would be absorbing energy from a photon, so absorbing light. But as it goes down energy levels, it emits energy. You can find the energy that it emits when it goes down 1 or 2 or 3 levels by taking the energy levels and finding the difference between the energy levels. Number 3A asks to calculate the longest wavelength. Okay, first off, we have to know which energy levels, jumping from which energy levels will give us the longest wavelength. In order to find the longest wavelength, we have to find the smallest amount of energy. So this also requires us to look at some equations. Okay, so the first equation that we're given in our data booklet is here. This is actually the only equation in this section, but we can change this equation to E equals hc over lambda. H is Planck's constant. I wrote Planck's constant over here on the side here. H is equal to 6.63 times 10 to the negative 34. Then we would multiply by the speed of light divided by lambda. The reason why you would multiply by the speed of light divided by lambda is because you can actually use another equation that we should know about speed of light. Speed of light is equal to lambda times frequency, and so we're just going to change this equation to frequency equals speed of light over lambda. And if you look at our original equation, we put this into our original equation here, and then it creates this equation over here that we need. So there's a lot of equations, like manipulation going on here. But then we have to take that equation and solve for lambda. So we're just going to rearrange some stuff to solve for lambda. All right, so which equation are we going to use? We're going to use this one. Lambda equals h times c over e. Now to find the e, again, you have to find the difference. I did write the differences in the picture here. So the difference between the lowest level, which is here, and the second lowest level is here, is 2.4, and that's the smallest energy transition that we will see between two levels. So that's going to give us our largest wavelength. So lambda equals 6.63 times 10 to the negative 34 times speed of light. By the way, speed of light is 3 times 10 to the 8 meters per second, divided by the energy of 2.4. All right. Now, we don't really care about negative or positive numbers per se. Like, it's all relative. So in this case, because we're going from a higher level to a lower level, we're emitting energy. We're emitting energy and emitting a photon of light. So this is going to be a positive number. There really is no such thing as negative wavelength anyways. And so we're just going to calculate this. Okay. This would give us the longest wavelength. So I'll put an L here for the longest wavelength. For the shortest wavelength, we would do the same equation again. But then we would divide by the greatest amount of energy between transition levels. And that would be here, the highest one and the lowest one. That would be 4.8. Yeah, That would be 4.8. So we put 4.8 in here. All right, if we evaluate that, we will get wavelengths of, let me just double check here, 1,550 nanometers. And we would get 258 nanometers. And the reason we want them in nanometers is because visible light is usually nanometers. Ironically, these two values aren't really on the visible spectrum, but typically we like to use nanometers because it could be significant if we're trying to figure out like what color it's emitting. This is going to be just outside the visible light, so ultraviolet light. Let's see, ultraviolet light would be a little bit shorter, so the shorter wavelength is ultraviolet, and the longer wavelength here would be infrared light. Part B says identify the atomic transition that results in an emission of a photon of energy level 4. Okay. When we look at all the possibilities here, and only one of them has a difference of 4, that would be the difference of 4 would be here to here. You can identify this transition by just saying negative 2.3 to negative 6.3. You would just draw an arrow here on the picture and identify that as the transition, or you can just simply say what are the two levels, and remember this is going down, so that's why it's negative 2.3 to negative 6.3. All of these transition levels are electron volts, by the way. Yes, I forgot one thing about the electron volts. You do have to convert the electron volts to joules. Completely forgot. So our equation is actually missing one thing here. So the conversion for electron volts is here. I wrote that here. It's 1 electron volt is 1.6 times 10 to the negative 19. So actually these equations need the conversion in the denominator. So I'm just gonna write that in real quick. So I'll put them in parentheses. 1.6, 0 times 10 to the negative 19, 1.6, 0 times 10 to the negative 19. Okay, so just to review, you need to do that conversion for energy. This equation requires the energy to be in joules, not electron volts. The energy levels are given in electron volts because that is just a basic unit that they like to use for energy levels. All right, so we've got our calculations. We have our equations here. So don't forget that this is the equation for wavelength based on energy emission. All right. Number 4. The emission spectrum of sodium contains two lines of similar wavelengths, 588.995 and 589.592. The lines are emitted in a transition from one of two narrowly separated EA, EB to another energy level EC, as shown in the diagram. Calculate the energy of each of the photons emitted. Okay. We see these wavelengths are very similar, but that's why there's so many significant digits here. There's 6 significant digits. So it's important that you use all the digits in your calculation. We're trying to solve for energy. We're going to use this equation here. So all we did was take the original equation, E equals HF. So here, I'll show you. We took the original equation, E equals HF, and then we substituted in C over lambda for F. Okay? So we see that this variable was substituted in here. All right. Then we get this equation here. This is the equation we're going to use. We don't own the energy, but we do have the wavelength. This is Planck's constant again. So lots of exponents here. That's a 4. Make sure we know that that's a 4. This is speed of light again. 3.0 times 10, 8. And then we have the lambda. So the lambda for each of these are, the first one is 588.995. 588.995. That is in nanometers, so you got to convert that times 10 to the negative 9. Okay, so just be careful. We got lots of exponents here. Okay, that's going to give us an energy level of 2. Well, actually, it's gonna give it to us in joules. Hold on a second. The answer in the answer book happens to be in electron volts. Calculate the energy of each of the photons emitted by sodium. Right. So the equation in the book gives it in electron volts. You know, if you're doing a multiple choice question and the question is in electron volts, yeah, you're gonna have to convert from joules to electron volts. So we have this conversion here. Okay, so whatever energy you get here, you're going to have to convert here. Electron volts. Okay, it ends up that we get two energy emissions that are very close in electron volts. We got 2.10528 and we got 2.10315. So then the question asks what's the difference, and then we can do the difference in okay, so it's a lot of zeros here. 0.00213, which ends up being 2.13 times 10 to the negative 3. So there's a conversion here. So, you know, should you put your answer in scientific notation? Usually, yes. Sometimes we use electron volts. Sometimes we use mega electron volts. You know, to be honest, it changes. And when we're talking about energy levels, we usually talk about electron volts, not mega electron volts. So electron volts is pretty standard when talking about energy levels. Okay. All right. So something to reiterate here is that if the energy increases, the frequency increases. If the energy increases, the wavelength decreases. So it makes sense that the longer wavelength represented here, so this is the long one, has more energy, so bigger energy, and the short wavelength, I got this backwards. The short wavelength here has more energy, and the larger wavelength here has smaller energy, okay? So this is the bigger energy. This other one is the smaller energy. The energy is the drop from here to here. And so there's less of a drop from here to here, so that's why there's less energy here. And then the wavelengths are given. Okay, all right. So it's inverse relationship is what I'm trying to say. So short, so lambda short, lambda long, energy, more energy for lambda short, less energy for lambda long. All right. Number 5 is a question about absorption spectrum. Okay, so absorption spectrum is when there is a light source that shines into a cold gas, and you're observing the absorption of the cold gas, of the light into the cold gas. So imagine there's a light bulb here. Okay. And the light bulb emits white light. And then you've got cold gas here. So this is cold gas. The light shines into the cold gas, and then the cold gas absorbs Okay, so the cold gas absorbs the light that is specific to that gas's spectrum. The absorption, the light that is absorbed appears black lines on a rainbow background. Now this is different from a hot gas because a hot gas shines colored lines on a black background. Okay, so it's important to know the difference between those two. This is shown in the notes. If you look at the notes, you'll see a colored background with black lines is absorption, and colored lines with a black background is emission. Provide evidence for discrete energy levels of the atoms of the gas. So when you shine this light through the gas, you'll see black lines, and the black lines are discrete. And so because the black lines are discrete, we know that they represent discrete energy levels of the gas. Part B can be used to deduce the chemical composition of the gas. Okay, so these lines represent wavelengths of light, right? This is wavelength 1, 2, wavelength 3, and those wavelengths are like a fingerprint that we can observe, that we can record, and then use that record of a known gas to identify other gases that we see. So like if we know the gas is helium or hydrogen and we observe these lines, we know that those lines would be consistent with any time we see helium or hydrogen. So the spectrum, the specific discrete lines on the spectrum is like a fingerprint of the gas. So that's like something we say about gases and their spectrums, their fingerprints, because they identify the gas. Okay. Number 6. The diagram shows some of the energy levels of an ionized mercury atom. I drew some work in here, but you just notice that the energy levels are more negative as you go down. Okay, so the lowest state is the least amount of energy, and as you go up, you're absorbing energy, and as you go down, you're emitting energy. Okay. State how many absorption lines can result from the atomic transition between these energy levels. Okay, so I guess I can write 6A here. We know that there's 3 possible combinations. I drew them on the. Whoops. There's 3 possible transitions. You can't get more than 3 because if you look at the picture, you get the lowest one to the highest one. Sorry. You get the lowest one to the middle, you get the lowest to the highest, and then you get the middle to the highest. So it's 3 possible transitions. On a copy of the diagram, draw an arrow to indicate the atomic transition that gives rise to the absorption line of the shortest wavelength. So we already mentioned this, so let's just mention it again. If it has more energy, it has more frequency and less wavelength. So it's asking for the shortest here. So if you want the shortest, then we actually want to find the most energy. Okay, so which of these is the most energy? Well, you would assume the longest line is the most energy, but we can calculate that out. The top to the bottom is -5 to -2.74, right? And that is clearly just more than -5 to 3.76 or -3.76 to negative 2.74. Okay, so on a copy of the arrow, draw arrow. Yeah, so we drew an arrow and I circled it with a blue box. Part C, show that the line in part B has a wavelength of about 550 nanometers. Okay, so we're going to use this equation. Just a reminder that we have to convert here to energy. Okay, so for here, let me start labeling things here. So this is part B, and this is part C. We're going to use this equation. Let's see here. We're going to use this equation. We're going to plug in H, C, and lambda. For lambda, we're going to put in... Oh, wait. Actually, it says show that the line has a wavelength. So actually, we have to calculate the wavelength and see if it's close to 550. So, all right. Sure. Let's change this equation. I don't have a lot of space here. So let's change this equation to this. Lambda equals H times C over E. The energy transition, which we did find in B, was going to be, oh, let's see here. It's going to be 2.27 electron volts. So you have to convert this 6.63 times 10 to the negative 34 times speed of light divided by 2.27 electron volts, but then you have to convert it to 1.6 times 10 to the negative 19 joules per electron volt. Okay, and then when you solve for that, you should get a number like this. All right, so we should get lambda equals this. And then the question is that 550 nanometers? And it is. The thing is, we're just kind of, this is decimal here. We're just used to, we just have to change this to nanometers. So, you know, it's kind of interesting to change something to nanometers. Basically, you just shift this over 2 spaces to the right and change this -7 to a -9. And then that's nanometers. Okay? All right. Number 7 is about a laser. It emits a wavelength of 633. Calculate in joules the difference between the energy levels. All right, so you're just going to plug this in. You plug this in to this equation here. So, let's try to shift this stuff down here. So, yeah, you just plug this in. Shift that down here. You're solving for, calculate in difference. You're solving for wavelength. So we use this equation again. Hold on a second. Oh, no, we're solving for energy. I'm sorry. Okay, so it doesn't really matter which one we use here. 7a. Okay, so we just use that equation. We solve for the energy. The energy happens to be... so I've done this equation several times. The energy is 3.14 times 10 to the negative 19 joules. Okay. Calculate the difference between energy. Yeah. So we just plug in. Yeah, we just plug in the values. Okay. Part B, what's the energy? What's the power of the laser? So the output power is 2.5. Estimate the number of photons the laser emits in 1 second. So we're actually going to use, so for part B, we're going to use the power equation. We're going to take this energy that we got here, and then we're going to plug this in to this equation here. And it's energy per second, okay? But the question is really how many photons are there? So we've got 2.5 times 10 to the negative 3 watts. And that watts is produced by photons that have an energy of 3.14. So how many photons do we have? So we put X is equal to the photons. Well, that's a lot of photons, right? We're going to solve this with 1 second on bottom. And then that's the number of photons.